think of a number line, and it's divided by the number 7. So below 7 we have acids, and above 7 we have bases. So at a pH of 8.6 and higher, we're going to have a base. That means we're looking for a formula of a base. Looking on reference table L, common bases, we'll see that potassium hydroxide is indeed a base. The next question, we're looking for a 100-fold increase in the concentration of hydronium ion. Now, hydronium ion corresponds with acids. So we are looking for a move in the direction more towards the acidic pHs, or a lower pH. That immediately eliminates the choices where we have a increase in pH. Now we need to decide which represents a 100-fold increase. Every move in pH is represented by a 10-fold increase. So 100-fold is going to equal 10 to the power of 2. That means we're looking for a pH difference of 2. That makes choice 3 the best answer. For the next question, we're trying to describe something with a pH of 9. Again, we go back to the number line, and we notice that 9 is in the basic region of pH. Now, here we're to compare the hydronium ion concentration to the hydroxide ion concentration. Now, acids have more hydronium ion concentration, and bases have more hydroxide ion concentration. In addition to a number line, we can visualize the hydronium ion and hydrogen ion concentration using this box. Again, the number line is represented at the top, where neutral is 7. Now remember that acids have more hydrogen ion concentration than hydroxide ion concentration. At 7, the hydrogen ion concentration and the hydroxide ion concentration is roughly equal. And at 14, the hydrogen ion concentration is much smaller than the hydroxide ion concentration. So again, the size of the letters represents the concentration. So we'll see that at pH of 9, there's much more OH than there is H+. Now that we can eliminate choices 1 and 3, we now need to refer to reference table M to differentiate between choice 2, turning Lipness blue, and choice 3, turning methyl orange red. So when we look for methyl orange will turn red when it has the pH to the left or lower. And since we're talking about a base at a pH of 9, choice 4 cannot be the correct answer. Choice 2 is best because we see that Lipness turns blue at the pH of 8.3 or higher. The next question has us referring to the level of acidity. As we remember from our number line, acidity involves pHs of below 7, and basicity is above 7. So if we want to have the most acidic solution, we want to have the lowest possible pH. So in this case, the only acid pH is choice 1. The next question is simply a reading comprehension question. And here we can see that normal rain has a pH between 5 and 6. So after we add quicklime, the hydrogen ion concentration should be some value between 5 and 6. The next question involves the word titration. So here we can see they give us a lot of data and they ask us to calculate the molarity of the acid. So to do this, what we're going to do is we're going to use reference table T. So reading the question, let's see what information they've given us. They've given us a 20 milliliter sample of acid rain. That is going to be our VA. And it is neutralized with 6.5 milliliters of 1 molar sodium hydroxide. So this here is going to be our VB, our volume of base, and here is our molarity of the base. So now all we have to do is substitute into the equation. The next question asks us to determine which solution is basic. Again, we return to our number line. Remember that 7 is the difference between acid and base. Acids have pH lower than 7, and bases have pHs of greater than 7. So the basic solution here would be pH of 12. The final question asks us to evaluate what's occurring when we change from a pH of 5 to 3. So again, we can use our trusty little rectangle. So when I'm moving from a pH of 5 to a pH of 3, I notice that the hydrogen ion concentration is increasing. Now recalling that the hydrogen ion concentration changes by 10 with each step in pH. A difference of 2 spaces is really 10 to the power of 2, or 100 times the original content. On to practice problems. So here, we're looking for the volume of a known solution to determine the concentration of another solution. So here we're seeing if we can find an equation that has something to do and it has 2 volumes. So again, we're referring to reference table T. And as you can see, the titration equation fits perfectly. In the next question, we're asked why hydrochloric acid is indeed an acid. So when we look at hydrochloric acid, we have to remember the Arrhenius definition. Now we can also refer to our reference table for hints. On reference table K, we find the common acids. And amongst the common acids, we see hydrochloric acid, and we notice that it has both hydrogen and chlorine. But when we look at all